I'd like to welcome you all to the latest installment of the SLAC public lectures, socially distanced. Please excuse us, but it's still the situation. Most likely we will have one more of these socially distanced lectures at the end of July, and then we'll see what the situation is in the fall. It would be great to see you folks all in person in the big Panofsky Auditorium, but we don't have yet the permission to do that. Today, we're going to hear a very interesting lecture by Arianna Gleason, a staff member at SLAC. I'll talk about that in just a moment. But first, I'd like to call your attention to two features, which if you put your cursor at the very bottom of your Zoom window, you'll see. First of them is the Q&A. So if you have a question during the talk, please type it into the Q&A. And at the end of the talk, we'll have 20 minutes or so with Arianna and two of her colleagues listed here as panelists to answer these questions. And yeah, don't be afraid to stray outside of the narrow bounds of this lecture. These people have their minds open, so let's find out what they have to say about your question. The second thing is you will see a CC live transcript. So if you push that button, you will get closed captioning. I've had some experience with Zoom closed captioning. It has gaffes, so just don't laugh too loud, but we hope that for those people who need it, it will be a useful feature. So please avail yourself of those two buttons at the bottom of your Zoom screen, and we look forward to your questions at the end of the talk. Okay, well, now let's get started. Arianna Gleason is a staff member here at SLAC at the Linac Coherent Light Source, our free-electron X-ray laser, and a member of the HED, High Energy Density group here. These are the people who basically irradiate things and study matter at extremely high temperatures and pressures, and why that is relevant to the origin of life is more or less the subject of this talk. Arianna got her PhD from Berkeley in 2010, actually in Earth and Planetary Science. Then she went to a postdoc at Stanford, to Los Alamos National Laboratory, and there she worked on shockwaves and materials, and then she joined the SLAC effort here on high energy density. She's an expert on visualizing the behavior of material under really extreme conditions, and you'll see a little of that in this talk. Actually, an interesting part of her career occurred earlier as an undergraduate. She worked as an undergraduate astronomer with the Space Watch project at the University of Arizona, and actually discovered some comets and asteroids that are now named after her. So her name is in the heavens, and we will see more about that in the course of this lecture. So Arianna, please take it over. You'll tell us about the shocking origin of life with meteor impacts and extreme conditions of chemistry. So thank you very much.
Thank you, Michael. And welcome to my friends and colleagues and visitors who are attending this lecture. I'm very privileged to work here at the SLAC National Accelerator Laboratory. I also have a position in the Geosciences Department at Stanford as an adjunct faculty. And I'm very lucky to work with such an extraordinary group of scientists and colleagues, two of which I am fortunate enough to have here. So please stay tuned for exciting discussions with Dr. Richard Walrath and Professor Richard Sandberg at the conclusion of this talk. And so diving in to one of the most exciting questions and exciting challenges of our time, thinking about the origin of life and the different ways in which scientists are pursuing this question. It can be thought of very broadly in a philosophical sense, in a religious sense, but also in a scientific and origin sense. And aspects of that we will discuss today. But first, I'm going to share with you a little of my own origin story As Michael mentioned, I have always been excited, intrigued by the heavens, and in various opportunities, even in my younger early days, of which I have an embarrassing photo in the upper left, attended some astronomy summer camps that extended into really fantastic education and experiences at the University of Arizona, where I did my undergraduate work and was fortunate enough to work with a team called Space Watch. And there we studied and cataloged near-Earth asteroids. In working at the Kitt Peak Observatory in Arizona, shown here above my head, here's a photograph I took from the top of our 1.8 meter telescope that was used to survey the skies. I was lucky enough to be bestowed with a named main belt asteroid, so-called asteroid Gleason. And during my time with those surveying, I found a comet. So there's a fuzzy little image here in the center of your screen, and it turns out to be a long period comet. Here's a much younger picture of myself at the 36-inch telescope so many years ago. And this interest in the location and origin of these bodies actually translated into my pursuits later in my graduate school career and postdoctoral career. In the early 2010, I joined the Extreme Environments Laboratory here on campus at Stanford. Here's a photograph of that. The team there, we study rocks and minerals under extreme conditions, high pressure, high temperature, that mimic the conditions of the inner planets, the inner core, and other terrestrial bodies. And that is an exciting way to investigate how matter transforms at these extraordinary conditions. And later on, I've been lucky enough to join the HED, High Energy Density Group here at SLAC, where I've continued this work and coupled this interest in location and identification of these comets and asteroids into finding out what are they made of and how could this be connected to the origin of life. So here is an outline for this evening's lecture. First, we'll talk about the different hypotheses around the origin of life. You might be familiar with some of these. Very exciting and ongoing active area of research. Next, we'll talk about what are we doing in our laboratories here at SLAC to investigate one of these hypotheses, so-called the impact synthesis hypothesis. In order to do that, we have to be able to visualize dynamics and changes in the meteoritic material, in the chemistry and the chemicals involved at very fast timescales. So we need a high rate, ultra fast camera. And that's something that we can do here at SLAC. And then in the end, I think the punchline of the entire story here is that in fact, life, at least primitive life, may be more common than we previously thought. So to sort of step back and consider the broad picture, exobiology and the search for life, is anybody out there, is an exciting and grand challenge, especially of our day. And we need to consider what is in that recipe, what is required. Well, we need the materials, in fact, the planets that provide habitability for life. We need the appropriate chemistry to kick us off. What's in that recipe book? What are the building blocks in a chemical sense that enable life? Water, liquid water is in fact one of the main ingredients, and understanding where liquid water is present in our solar system and in other locations is also very important. And then finally, energy. In order to kickstart, actually seed what is the building blocks of life to go from abiotic to biotic requires energy. And the different hypotheses toward investigating which one is the one hypothesis and that energy deposition into a system is part of what we'll discuss here today. And I think the punchline is primitive life, or life, is actually far more common. I think that's a very exciting notion. So if we zoom all the way out and think about where we are in the universe, in fact, the Earth is 14 billion years old. So the laws of chemistry and physics have had an awfully long time to try to get this recipe just right. And in the universe, there are hundreds of billions of galaxies, and that's just mind-blowing. But more than that, each galaxy has about 100 billion stars. Okay, so that's also an extraordinary number. And each of those stars could be considered as a sun. Now, most stars have planets. And over the recent years, so many exoplanets have been discovered. In fact, there are searches you could do to look up how many exoplanets have been discovered and confirmed. And just recently, I looked up this number. Over 4,000 exoplanets that are near the habitable zone have been discovered and confirmed. Of those, 60 or more, this is likely just a limit of what we understand, 60 or more are just right in that Goldilocks regime, that habitable zone that has the appropriate chemistry and energy required. And the laws of physics and chemistry are the same everywhere. So this really positions this question well to say, oh my goodness, life, primitive life, is far more common than we previously thought. So let's talk about what are the requirements. What's in this recipe book for life? And how does something go from very simple to very complex? So here on this graph, I show in the upper right-hand corner, the simple side. So we'll start there and let's walk through one by one, all the way to complex. And you may be familiar with terms like amino acids or RNA or DNA. DNA is the holder of the genetic code. It is the indicator, as it were. And so how do we build up this complexity? Well, there are very common, a set of common elements that are required to begin this process. That is carbon, hydrogen, oxygen, and nitrogen. And we are fortunate, it is fortunate that this is in abundance in our solar system. Each of these elements is in abundance in our solar system and across the universe. And these different elements can come together to form very simple molecules, which I show here. CH4 methane, which you're probably familiar with. Some of us produce it from time to time. NH3 ammonia. This is, think of it as a window glass cleaner. Water, liquid water is, of course, necessary and paramount. Carbon monoxide and carbon dioxide. That's what we produce when we exhale. These very simple molecules can come together in more complex ways. And so what do I mean by complex? I mean the ability to build up these very fundamental building blocks, amino acids, that are found in RNA. And so let's look at this next piece. So the simple molecules that we've shown here can in fact break apart and reform in certain ways to produce the 4 nucleobases of RNA. Then we need to think about an additional level of complexity. So we've gone from simple molecules that we're familiar with to something more complex. But now it comes to the structure of this RNA that then leads to DNA. The structure is a helical structure, right? And it's a chain. So we also have to consider how these molecules are building up complexity chemically, but structurally in order to satisfy these requirements. And it turns out the structure is key. And we'll see that, we'll revisit that topic of structure and how different surrounding material, maybe host rock and mineral material, provides that template, that image required for building up these chains of more complex nucleobases in the RNA. So templating. You may be familiar with something called biomineralization, where biological materials are found commonly on certain minerals and rocks. And this is a very fascinating area of research, wherein on the surface of a mineral or a rock, there's a certain surface affinity for different bonding, different chemistry. And what can happen is there can be an encouragement, an enticement of perhaps some of these very simple molecules to build up its complexity, so-called synthesis polymerization, right? And self-assemble in that particular structure. And that might actually be one of the key ingredients that need to be considered when looking forward to the possibilities and the origin of life. So there are several hypotheses that have been put forward and commonly discussed in the scientific community around how to build up the complexity required. The first one you might be familiar with, so-called the Millerura experiments, which took place in the early 1950s. It is essentially the combination of simple molecules and a bolt of lightning. So it's lightning striking a pond, as it were. So this experiment, there was a requirement of some water vapor, liquid water, and then water vapor in the presence of these very simple molecules we mentioned earlier. And then there is a bolt of lightning or a strike from an electric spark that enables these materials to break apart. The simple molecules disassociate and reassemble in a more complicated fashion. And this experiment was very exciting. And in fact, the organic molecules, the materials that were formed did indeed craft the amino acids that are required, the ones that are exactly required for life, okay? In fact, there are over 70 different kinds of amino acids, of which only 20 are in our biology here. So that's interesting that there's actually a wider variety of amino acids than actually what life uses in the biological construction. Another hypothesis that's been put forward, again, you may be familiar with extremeophiles. So microorganisms and materials that are actually thriving, not just surviving, but thriving in extraordinary number in the locations you may least expect. One is so-called a black smoker. This is a region in the depths of the ocean where the crust is being pulled apart and there's an upwelling of hot magmatic material. As this magma upwells, tremendous heat, geothermal heat, is input into the system, and there's an interaction of metallic minerals, high Z minerals, in concert with the circulating seawater. This environment is ripe for spurring on these extremophile microorganisms. You may also be familiar with hot springs, where differences in pH, very acidic, very basic, can actually generate these beautiful colors that we may view. And in fact, there are rich colonies of extremophiles that persist in these unusual places. And then we arrive at today's topic, which is an impact type of synthesis. Here we consider the fundamental materials, these simple molecules, as ride along as participants that ride along on different kinds of rocks and minerals in space. We could talk about collisions then of these different components, collisions or impacts between dust grains, between meteorites, or even as large as asteroids and materials that build up to a planetary scale. And it's this input of energy during that impact event, that dynamic process during the collision. It's very short-lived, but it has an extraordinary amount of energy. Could that be the input of energy required to break apart and have the molecules rebuild in a more complex way? That's what we're going to explore today. And we're going to use as our vehicle in this case to consider meteorites. Now, meteorites are a fascinating area of study in and of themselves. In fact, there's quite a bit of diversity in meteoritic material. And a meteorite is a rocky remnant of an asteroid or a comet that falls to a planetary surface. In fact, we have meteorites that have come from Mars, and that's a wide area of exciting study. Here, we survey the different types from so-called chondritic material. This is very carbon-rich meteorites, to iron meteorites. You may have seen possibly a slice through one of these, and the different minerals actually separate from one another, making this beautiful interlacing sort of finger pattern. There are also meteorites, so-called palisite meteorites, that have both components of a rocky planet, meaning both silicate rich and iron in the same material, in the same meteorite. And then you go all the way to achondritic, meaning absence of carbon rich components. And these meteorites are messengers mixing across the solar system. In a sense, you could think of them as the solar system Uber, right? They're moving material around from point A to point B. They in fact contain, meteorites have been examined that contain all 70 amino acids. So let's just pause right there and take that in. Meteorites have fallen to the earth that already contain the building blocks of life. Okay, so this is very exciting. They contain a wide range of organic material, not just the very simple molecules, but in fact, manifesting this buildup already of the complexity. We are going to then consider what's required. What's that recipe for life look like in the context of meteorites? So we've got here on this image information that tells us from the study of different meteorites that actually these meteorites have sourced their amino acids from different regions in the solar system. So there's an incredible opportunity for the prebiotic materials present already. There's also, through the impact and collision process, there is a mechanism to go from simple to complex through that shockwave and impact process. And we're going to walk through exactly what that means in a moment here in the talk. But the last thing that I want to draw your attention to is the mineralogy itself. The minerals within these different meteorites may hold the key for how that complexity is built up in just the right way. That helical shape that is a part of RNA, and the other complexities enabling the chain to go from individual amino acids to a more lengthy chain and building up of the complexity. That might be enabled, in fact, by the minerals themselves. So understanding how those minerals change during that impact process might give us incredible insight into, in fact, what kickstarts that origin of life. So previous work has investigated this very question. And in 2014, there was a study done where they began with a very simple molecule. It's called Formamide. Okay, so Formamide is actually quite common. It's found extensively in interstellar clouds. So it's very common in space, and a good source material. It also can form all 4 nucleobases, okay, that are required and is a constituent component of RNA, okay? So all 4 required nucleobases can form. But how do we get from formamide to the nucleobases? Well, a concept was put forth by these colleagues, or this work in 2014, suggesting that an impact or a high collision, high energy density process, such as a collision, could generate the complexity required, break apart this formamide, which is oxygen hydrogen, and nitrogen, break it apart, and in that dynamic process, reassemble to more complex materials. And this idea is also put forward by a colleague of mine who's joining us as a panelist, Dr. Richard Walrath. And so I want to be sure and extend the notation to him that this is part of our collaborative idea and his idea as well. So this work in 2014 from previous investigators, they sent in a high power laser. They wanted to blow stuff up, right? Break that formamide apart and then visualize, watch what happens in time to see the actual development of the more complex material. But the issue may be that their camera, their way of visualizing the complex buildup wasn't quite fast enough. And that key aspects of that are actually missing, and we don't know, we can't see it yet. And that's where the tools at SLAC can come in. So what are our tools that we use to investigate these very extreme conditions and the materials at extreme conditions? Here I show a view graph that illustrates some aspects of high pressure you might be familiar with, such as a can of soda. So at ambient condition, where we are here, let's say at SLAC, or you are watching me through this webinar, the can of soda has in it carbon dioxide that's been pressurized to lock it in. So when you open it, you hear the release of that CO2. You might be familiar with high pressure in the sense of helium that supplies your balloon to lift for a birthday party. You may be aware of increased pressures at the base of the ocean, that a tremendous column of water pressing down. There are other ways to generate extreme pressure. Thermonuclear testing. There's also extraordinary pressure at the center of the Earth. In fact, 3 million times our atmospheric pressure, okay? That's an extraordinary number to consider, but these are the pressures, these are the conditions that are at play during these collisions. Of course, there's much higher pressure, certainly at the center of larger planets, Jupiter, and of course at the center of stars. And we have a set of tools here at SLAC and across the globe to mimic those same pressure and temperature conditions. And I show these at the bottom, from very simple pressure vessels that can exist in a laboratory to ton presses that bring down additional pressure up to several hundred times atmospheric, to something called a diamond anvil cell, and so on and so forth, until we get to lasers and the ability of lasers to actually generate high pressure in a material. And this is essentially around the regime where we will focus today. And in fact, the pressure regime we are considering for this work is somewhere right in the middle, below and above 3 million times atmospheric pressure. So it's a tremendous range to try to access, but we can do it. And so we've talked about impacts, we've talked about collisions, and part of what happens during that impact process is the generation of a shock wave in the material. So what is a shock wave? Well, let's think about a train, a set of train cars in a row, happily moving along. But all of a sudden, the brakes lock on one of the train cars, and it comes to an immediate and abrupt stop. What does that mean about the train cars behind them? It will too come to an immediate and abrupt stop, and there's a chain reaction of halting of the train cars. This is essentially the same idea as in a shock wave that moves through a sample. It is a supersonic wave that moves through a material, generating a mechanical or a pressure discontinuity. On one side of the shock wave, the sample is perfectly happy at ambient condition. On the other side, there's a tremendous jump in pressure. And this is what's illustrated in this train car. You have train cars that are moving forward and train cars that are immediately at a stop. And the material properties on either side of that shock front are quite a bit different. And it's the change in the material properties that might be the key to templating the appropriate structure for the complexity of materials we're looking at. But how do we visualize that? A shock wave, as you might consider, supersonic wave speeds are far faster than we can visualize by looking using a suite of different cameras. So imagine this. Imagine a horse is galloping. And in fact, back in the day, there was a bet about how does a horse gallop? Do all the hooves come off the ground? Well, if you only have the starting image and the final image of a horse, you don't have any information about what's going on in between. You have A and B, but you don't know what happened in between. So you need a camera. You need a set of images or a way to visualize what is going on in between A and B. And so to solve this bet that was placed, a fellow named Muybridge set a series of cameras and tripwires to track and take images of a horse galloping. And in fact, you see here in the second and third image, all the hooves come off the ground. But they wouldn't have been able to satisfy and come to that conclusion unless they had a camera at the appropriate speed. And so that's the key here, to see the to visualize the simple molecules breaking and reforming at appropriate timescales. We need a fast camera. And so that's why we want to use and can leverage tools here at SLAC. And so I introduce you to LCLS. This is the Linac coherent light source. It is an X-ray free electron laser. So what does that mean? It means it can generate X-rays that are laser-like in property, okay? And we'll get to a few of those in just a second. But it is essentially a 2-mile-long camera that can zoom in and have like you're riding along right with the atom as it's undergoing some dynamic process. And it gives scientists a very unique tool to study a suite of dynamic processes, of which this origin of life is just one. So a couple terms will come up in the following slides related to timescale, okay? So a nanosecond is about on par with how quickly your computer runs. So you may have a gigahertz based computer that's about 10 to 100 nanoseconds to process different activities. So a nanosecond is the amount of time it takes light to travel about 1 foot. However, the X-rays produced by the LCLS are a femtosecond. So that is 1,000,000 times faster than a nanosecond. It's about the length of time it takes light to travel the width of your hair. So it is the appropriate speed. It is the fast shutter required to witness the chemical dynamics and the materials processes at play. And I want to mention also that the brilliance and the coherence of the LCLS is an aspect that enables this work. So we are able to visualize the changes in the chemistry and the materials that are required because the X-rays have these certain laser-like properties. Okay. So we've got our fast camera, but now we have to generate a shock wave. We have to actually bring about that deposition of energy into the system. And we do that by using an instrument here at the LCLS. And that instrument is the Matter and Extreme Conditions instrument. And essentially, we bring in high power lasers to blow stuff up. And if that's not exciting, I don't know what is. So this is an opportunity we have to leverage high power lasers, and we go through an ablation process, which we'll walk through here in a moment. But this is a schematic of the instrument that we use and other colleagues use. So you see here in yellow, the path of the X-ray beam coming from left to right. And just above my head is this chamber. And this is where we place our sample material and where the large lasers come in and interact with our sample. And there's a stick person there for size. So it's a bit taller than myself. And it is appropriate, or we are able to crawl inside and place our optics and be engaged in the experiment, which I think is really a unique opportunity. And this instrument is critical to a number of different disciplines, not just in shock physics, but also in plasma physics and high pressure mineral physics and warm dense matter. So how does this experiment actually work? In the view graph here, in the center of the image, are a set of targets. So let's say these are the meteoritic material. My large laser comes in, and by the way, that laser deposits as much energy as is in a bolt of lightning. And it does that in a nanosecond or a few nanoseconds. So if you recall the movie Back to the Future, and Doc says 1.21 gigawatts. Well, that's exactly what we're doing here in the MEC instrument. We send in this amount of energy, as much as is in a bolt of lightning, and we're going to perturb our sample. But here's the best part. We get to use Newton's third law, wherein for every action, there is an equal and opposite reaction. So here I show an image of the sample, and these two lasers are coming in. Here we happen to use two lasers, but here we come in and they are incident on the sample. And we have Newton's third law, which means as those lasers are incident, a plasma, an ablation process, material is blown off. As it's blown off, these little yellow dots, that's my material blowing off, a plasma is forming. I'm going to launch a shock wave in the opposite direction. In this case, the two shock waves are going to come together, okay? So this process is going to compress instantaneously my material. So our lattice, the structure of the mineral, will go from ambient condition to something highly compressed in nanoseconds. And we want to visualize that process using the LCLS. All right, so we bring in the X-ray beam. Here I show that a schematic, we have this compressed material. And now here, I bring in my X-rays and I probe at just the right time to view what's happening to my sample. I then record using a series of diagnostics, information about how my structure and sample is changing. And then I'm able to take that information, that data, and come up with a structure, let's say shown in the upper left, of exactly how the atoms and molecules are now packed together once they've been compressed. So we're going to leverage that kind of tool in 3 different ways to get at this question of the origin of life. We're going to use Xray imaging to follow that shock wave that moves through. We're going to use X-ray spectroscopy to actually look at the chemistry. How are the bonds between the molecules in the formamide, let's say? Remember, that was that key, very simple molecule that serves as the predecessor for these potential 4 nucleobases. We're going to look at how the bonds change in real time. And lastly, we will look at how the lattice, the mineral structure, is modified that perhaps can accommodate the templating or the structure required to build up the complexity in those biotic materials, excuse me. So first we want to visualize and see the shock wave. So what do we mean by X-ray imaging? Well, you might be familiar with going to the doctor, and X-rays are passed through some part of your body to visualize perhaps a broken bone. It's the same kind of idea that we're using here, only our images are taken ultra fast, and they use those unique properties of the LCLS, meaning the coherence and the brightness. And so here I show actually some new data, some recent data This data was processed, in fact, by a graduate student working with Professor Richard Sandberg. And here we show a sequence of images. So on the far corner, we have a sample with a void. So that circular feature in sort of the upper right, and it's listed as t equals 0, meaning it's time 0. It's just sitting there, right? So we have a void. This example, in fact, does not contain formamide in the void. So this is the null case. So we have a sample. From the top of the screen to the bottom of the screen is the shock compression direction. So I'm going to send in that drive laser and I'm going to generate a shock, right? I'm going to generate a tremendous amount of pressure in a very short period of time. And so we're going to see as we step through at 2.4 nanoseconds, at 4.5 nanoseconds, and at 8 nanoseconds, there are different linear features. You see white lines that move across or that are located at different positions in the image. We are able to track at that nanosecond time scale the motion of that shock front as it moves through the void. So now imagine the next experiment is going to be, we have the void now filled with the formamide material, that starting component that could be so critical. So this is very exciting preliminary work, and we have a number of students and postdocs who are working on this topic, and we're very lucky to have that sort of opportunity with them. So we're able to witness the shockwave move through. Okay, but now we want to understand what's going on the chemical side. We want to understand and visualize how those bonds are being broken and reformed. And here we're going to use a different technique to see that chemical change. This is called X-ray absorption spectroscopy. So we send in a different kind of X-rays and soft, they're called soft X-rays, lower energy, a different wavelength. And these are just the right energy to interact and give us information about the bonding. So we're going to send in that shockwave. We want to watch how the bonds, how the chemical dynamics are modified during that shock process. And we can do that by looking at a soft X-ray absorption spectroscopy. In fact, there's an upgrade coming, or in the works, I should say, so-called LCLS2, the Linac coherent light source number 2, where we have superconducting Linac. So there are different kinds of linear accelerators. To date, we've mostly been leveraging copper Linac. It recently went through an upgrade actually to achieve very hard X-ray energies. But in concert with that, we are bringing on board superconducting Linac, and this will allow us to reach just the right wavelength of soft X-rays right at the carbon edge, one of the key edges for looking at these carbonaceous complex materials. And it's going to get faster. So in fact, we'll be able to leverage 1 million pulses per second using this new upgraded linear accelerator. So we're very excited for that. And we're going to combine that Linac, that upgrade, with dynamic compression. So here's a schematic where I show the drive laser pulses coming in to a meteorite sample that perhaps has been filled, the pore space is filled with the formamide. And then we're going to send in those femtosecond, those very short pulse length X-rays, just the right shutter speed, right, to see the dynamics in process. And part of the way we visualize that is maybe a change in the energy. So I show here fluorescence spectroscopy as well. So one color of the X-rays coming in is then modified. And that modification, that different color, tells us something about the chemical change. And finally, we need to understand what's going on with the host rock material. So we visualize the shock wave, we've looked at the chemistry, and now we want to understand the contribution of the mineral structure change to the templating, right? How is the material modified? And a way to track that, a way to fingerprint, if you will, how minerals are being modified, how the structure is changing, is by using something called X-ray diffraction. And so here, again, just the right wavelength, just the right energy of X-rays are going to come in and interact with the periodic array of atoms, the so-called this lattice structure. And when that lattice structure changes, we will see a different pattern arrive on our detectors. And every single mineral, every single one has a different structure. In other words, there's a unique fingerprint for every single one. So I can track that. I can visualize that fingerprint change, as it were, in real time. And so we've done this in the past. Some studies have been completed looking at silica, looking at quartz. And you might be familiar with this. In fact, the majority of the rocks, the vast majority of the rocks here on the Earth's surface are silicates. Feldspar is the number one, only second to quartz. And so we can collect this as our starting material and watch how the structure changes in real time. And in fact, we've seen how the bonds of the silicon and the oxygen in these silicates are broken and reformed at sites such as an impact site, where you can scoop up material and say, oh, you know what I find here? I find a different structure that's indicative of a high pressure event. And I can watch that take place using these high power lasers to generate the shock. And we've done that. So here's an example of a study where I have a sample of quartz or of fused silica, so-called window glass, as it were. And we send in just the right amount of energy to generate a shock wave. And when that shock wave is moving through our sample, I probe with the LCLS at just the right time. And so let's see an example of that. Oh, well, first, let's take a tour of how we do that experiment. Here is the MEC chamber. So in fact, the location where you can go in and position your optics, there's a target stage right in the middle, and we have our cameras downstream. And in fact, for some of these optics, these laser optics, they're 4-inch massive optics used to focus different parts of the optical laser. So again, very exciting stuff for all you young researchers out there. Here's the chamber, as it were. Again, a little person there for size. So it's certainly taller than me, but big enough so I can get in and crawl around. And here's an example of a photograph of the inside. So imagine you're able to crawl up in there and position your different optics. In fact, I saw colleagues and friends of mine doing that just today inside the MEC chamber. So it's a very active place where we can manipulate and place our diagnostics and cameras as we need. So here's an example of a starting material. This is fused silica. And the take-home message is that there's actually not much to see. Fused silica is amorphous, meaning it's a disordered structure. So that fingerprinting capability, looking for a specific pattern of intensity on a camera, we actually expect to not see any. Just above my head, you might see some black sort of pepper speckle patterns. This is damage on the camera. And so here we have our fused silica. It's just sitting there at ambient condition. And I'm going to send the drive laser in. I'm going to generate a shock wave. And then I'm going to probe at just the right time. And what happens? This beautiful pattern is collected. So what does this tell me? It tells me that my structure, my fused silica, my glass, the bonds between the silicon and the oxygen are breaking and reforming, so-called a reconstructive phase transition. And this is happening in real time in only a few, up to 12 nanoseconds, as I show here. Okay, so this is the kind of work that will be completed to study, to look at the origin of life, these 3 key aspects. The imaging of the shock wave that tells us how is the surrounding material modified? How is that shock wave modifying the meteorite sample? We want to understand the dynamic chemistry at that pore space where we're holding our formamide. How are those bonds breaking and reforming? And on what time scale? We suspect, based on previous work, that in fact, there's a critical missing data set at very short times where the most exciting chemistry is taking place. We need to see that. We need to visualize that. And finally, the third aspect of this is, how is the mineralogy changing? How are the minerals influencing that kickstart of life, that required structure of the nucleic acids that are formed? And with that, I want to then step back and realize that these processes are taking place all over our solar system, likely all over the universe. And this is an extraordinary time to be living in. Here we have sample return coming back from Mars. There are so many opportunities there and exciting new data sets coming in from different rovers in the studies that are undergoing for Mars. Other icy moons of different planets. Here's a visual of Enceladus, which is an icy moon of Saturn that has this beautiful so-called chaos structure, these cracks, these linear features that actually let us know that there's liquid water. There's water below the surface. And so there's so much opportunity for that required molecular component, that opportunity for the basic building blocks of life. And through these shock compression, through the dynamic high energy processes of collisions, we have that energy input to build up complexity. And moreover, I think the other piece that we're trying to focus on is how to provide the template, how to provide that blueprint, and the minerals themselves might be the key. So this is an extraordinary time to be a scientist, and we are very lucky to have access to the tools, but there's more to be done. So a message to the listeners out there is, this is so important for you to get engaged, ask questions. There's lots of opportunity for participation. And I really encourage you to reach out to your friends, your colleagues, and try to get engaged if it suits you. And with that, I'd like to leave you with this thought. You know, the history of humankind is marked on a timeline of discovery. And I think this is what's next. And with that, I'd like to acknowledge my extensive, fantastic collaborators. Here I list several names, many names, but there are many more. And in particular, colleagues here at SLAC who are just critical to the execution of so many experiments, colleagues at Stanford in the Extreme Environments Laboratory, many institutions, both across academia and national laboratories, play a monumental role in enabling these large team activities. And certainly I want to acknowledge my funding. Lots of this work is spurred on by the Department of Energy Office of Science, as well as NNSA, and certainly the National Science Foundation. And with that, I will conclude the main part of the talk. And I'd really like to introduce two folks who are highlighted here, Dr. Richard Walrath and Professor Richard Sandberg. So we are fortunate enough to have two Richards with us today, good friends and colleagues of mine, and a little bit about each one of them. Dr. Richard Walrath works here at SLAC now, an SSRL project scientist, staff scientist, but he hails from NASA. So he previously worked at NASA, and currently much of his work is focused on looking at lunar regoliths and using spectroscopy to study those materials. I also want to introduce Professor Richard Sandberg. He hails from the Department of Physics and Astronomy at Brigham Young University, but prior to that, he was a prominent member at the Los Alamos National Lab, worked on an extensive set of shock compression studies, and is an expert in X-ray optics and looking at not just materials at extreme conditions, but the fundamental tools required to visualize that. And with that, I think we will transition to the panelist. Thank you.
Well, Arianna, thank you very much. It's a really fascinating lecture. Let's just get rearranged. I think you have to unshare your screen and we'll go to a gallery view of the three speakers.
Sure.
And so, Carmen, you can.
There we are. Thank you.
There we go. Okay. Very good. So now we'll have Arianna, Richard, and Richard answering questions. I'm sure you have more questions. So please now look at the bottom of your Zoom screen. There's a Q&A. Type your questions in there and we'll answer them in turn as long as we have time. So actually, here's the first question.
Yes.
We all know that you can pick up a rock and say whether it's, from your sixth grade experience, a sedimentary or an igneous rock. It came from sediments or it came from volcanoes. Can you pick up a rock and say this must have come from a meteor?
That's a wonderful question, and I think it's all about the location of the fall, as it were. I know that a number of experts collect meteorites and other falls in strategic areas such as the poles, right, Antarctica, and you can easily see where rocks have fallen that are clearly out of place. There are other ways to test different rocky materials by looking at their isotopes. And so for a lay person or an individual to pick up a rock and claim without a doubt that it's a meteorite, I think there's probably only a few cases where that would be appropriate. One of which is if it's an iron meteorite. So it's just iron nickel rich, highly magnetic. That might be a clear path. I wonder if Richard Walrath, do you have other comments there on that one?
No, I think you captured it pretty well. It can be very difficult to tell definitively, as you said, that something is a meteorite, but there are certain clues or certain classes of meteorites like pallasites, which are so distinctive that they're obviously from meteorite origin. But largely speaking, there are missions where people go out to find them, and if you're a geologist to know how to spot them and know that this rock has no business being among a specific formation, but in general, places like Antarctica are great because it's all going to be ice unless you have a meteorite coming from somewhere else. So that's one of the reasons why NASA loves to go to Antarctica to source a lot of its meteorites.
Okay, very interesting. Someone out there would like to know, are there flat planets?
No. Maybe. Richard Sandberg, do you want to go for that one?
Yeah, I actually looked this one up a little bit. So I think the International Astronomical Union, right? You may have heard about their definition of planets, which they redefined Pluto as a dwarf planet. And one of those is that the planet is big enough, it has enough mass that its gravity kind of squishes it into a circular object or a spherical object. So I guess technically something that was flat, kind of like that meteorite was a Hammamia. I can't remember with the long skinny one that was coming out. That one technically is not a planet because it's not big enough. It's not orbiting the star and clearing. There's several definitions of a planet, but I guess we would say it's not really a planet if it's flat.
Yeah,
do you agree with that, Ari? Though I'm not a planetary scientist.
Yeah, you have to remember the Earth is flatter than a bowling ball. It's more spherical than a bowling ball.
Yeah.
So when you have something that big, gravity just pulls it all into the most compact shape. And when the planets formed, they were very hot, so it was even easier. But the asteroids have crazy shapes sometimes. Yeah. You've seen them.
They do. Yeah, we've seen, I recall a variety of photographs, some that are shaped like peanuts. So I think there are certainly different shapes, but it's true, as Professor Sandberg said, you know, once the sort of self-gravity, different forces at play encourage more of a spherical structure. Yeah, like a ball structure, exactly.
Andre Fils-Antoine would like to know, has there been any evidence to support the possibility of non-carbon-based life supporting chemistry? So you talked only about carbon-based chemistry.
That's right.
I guess there isn't much evidence one way or the other, but please, is this a possibility that we should think about?
Probably Dr. Walrath has more insight on that question.
To my knowledge, there's not been any definitive demonstration that you can have a silicon-based chemistry to support life. It comes down to, you know, there's a, from the chemistry perspective, you have to have the right energy for bonds breaking and forming so that you can actually synthesize complex molecules and then have them stick around for a long time to actually serve as something for life. So there's sort of like a narrow zone for, at least on Earth. Now, there has been some proposals, for example, nitrogen-based chemistries for life on a place like Titan, because it's so cold that you can actually form these sort of stable complexes formed purely with nitrogen-nitrogen bonds. Though again, that's, you know, whether or not that could actually give rise to life, you know, theoretically, we say something complex can form, but life is so complicated that it would be very hard to model it just on the theoretical basis. So short answer, experimentally, we haven't seen anything. Theoretically, there might be some other chemistries that there's some indication could work, but they have not yet been demonstrated to experimentally be valid for forming complex life.
Bob McMillan, actually, first of all, really enjoyed the talk. Thank you very much. He'd like to know about two other sources of energy that might play a role. First of all, cosmic rays, and secondly, solar UV radiation. Are those part of the picture or not?
I think actually Richard has done, you've worked a bit on the UV, or not worked a bit, but considered the UV input energy option, right?
Yeah, so UV is definitely something that's producing a lot of chemistry in our atmosphere. You know, the ozone layer you've heard a lot about is being formed by mostly ultraviolet and shorter wavelength light that's got a lot of energy up there. So I'm not an expert in that area, but I definitely have heard that that is a source that people have talked about. Cosmic rays, I don't know, that those are very, very high energy. There's cosmic rays that are, you know, many times more energetic than anything we can produce here on Earth. And so I don't know if that would kind of, you know, tailor-made take apart these bonds so they can go back together, or just kind of blow everything up. So I haven't heard a lot of discussion about cosmic rays, but maybe Richard Walrath or Dr. Gleason know more about that. But ultraviolet, I've definitely heard about that chemistry in the upper atmosphere.
Yeah, I've not heard of cosmic rays leading to this. I mean, they would definitely impart a lot of energy into a system. So if you have some molecules, they're going to break them apart, and we know that they can recombine and form some very interesting compounds. Like one of the things that Dr. Gleason was talking about in her talk was this idea of, you know, after an impact, you form this plasma and you get all these fragments and you recombine. So a cosmic ray could probably produce the same types of conditions. But, you know, they're very hard to produce in a lab. They're so highly energetic that's, you know, so we have a hard time modeling those experimentally, but presumably they are forming these kinds of alterations in the interstellar space, or not, sorry, in interplanetary space.
Bob would like to know if you can relate the energies created by impacts to the energies in your experiments. Is you're trying to reproduce this level of energy, or you're at a different scale?
No, in fact, the level of energy deposited into the system and the time scale are a one-to-one. So they are in fact the same. There are some discussions on, do you need so-called laser-induced dielectric breakdown, as in the Ferris et al. Article. So like truly generating a plasma of the material, and then sort of a buildup then of the more complex molecules, or if the passage of a shock in the context of several tens to hundreds of GPa, so that's 10 to the 9 pascals of high pressure, but also at many thousands of kelvins, 3,000, 5,000 Kelvin, and you do all of that in just an instant. And it turns out that the energy relationships are quite on par, at least from a modeling perspective. So we feel confident we can achieve that kind of energy deposition here with our tools.
Okay, Joel would like to know about this business of chirality that you brought up. Are you aware of any solid surfaces in nature that favors left-handedness as opposed to right-handedness, or vice versa? And alternatively, could we have life based on D instead of L amino acids?
I love that question. And I, by trade, I am not a biologist or really a chemist, as it were. But I have done some reading on this, and it's actually quite fascinating. I think the answer is we don't know. I don't think we could. Some of the minerals and the structures that have been put forth to encourage differences in chirality are clays. So one that was mentioned quite a bit is so-called montmorillonite. And this is a clay mineral that actually is quite common when we produce cement. So some of the materials of which the buildings are made, in fact, have the appropriate structure. It's in fact a very layered structure of these silicates. And depending on the slight differences in this layered orientation, it could be possible, I think, more step-by-step studies, more sort of visualization at that level, at the appropriate level of this lattice are required to answer that. For the other aspects of the chirality question, I wonder if Dr. Walrath has some more insight on that.
Yeah, I think you covered very well, how we can see how these things might be templated. In terms of, could we have life based on D amino acids? From a chemistry standpoint, the answer would be yes, but it would just involve everything being D. I mean, so the idea of chirality is that it comes from the term for handedness, right? So you have a left hand and a right hand. And, all of our amino acids all conform to one of those two. But in principle, the other enantiomer, as it's called, is chemically identical. In fact, separating out two enantiomers from each other is a very difficult thing to do because they are chemically identical. So you have to find lots of different tricks to do it. It's very important for developing medicines because they have to be enantiomerically pure. So yes, there's chemically nothing stopping it from having gone the other way. And there's the standing question in prebiotic chemistry: why did we go with L amino acids instead of D? Like, why did that become the dominant form? And I don't believe that question's been definitively answered yet.
Yeah, I just got to jump in here. I'm not in this field, but I'm an elementary particle physicist, and I'm kind of an expert in chirality and elementary particle physics. And so in ordinary chemistry, there's a symmetry that says if you have a left-handed structure and a right-handed structure, they just have the same chemistry. They're just mirror reflections of one another. It turns out that the radioactive decay is actually chiral. And there are a bunch of papers trying to prove that we're left-handed because of that. Personally, I've read those papers and I'm not persuaded, but it's still something that people debate. But the thing you have to think about is evolution. Once you have a successful kind of protein, which is left-handed, then it grows exponentially and it pushes out all the unsuccessful right-handed ones, or vice versa. And I think, personally, I think that's the most reasonable explanation. It could have gone either way. It's just a coin flip. Let's see. Ferguson would like to know, can you talk a little about the caching of samples being taken by the Mars Perseverance and when they will be accessible for further analysis?
Oh, that's a great question. I don't happen to know. I'm actually going to delegate that to Dr. Walrath, who may know more on the NASA side.
Sure. So I was actually fortunate to be at a conference recently where they were talking about this very question. And the answer is that the Perseverance rover is going to go around as a special caching system for drilling and storing samples within the rover. And then there's going to be a separate fetch mission. So the Perseverance rover did not land with the way to get back. And the reason for that is we want to take our time collecting samples, selecting which samples are the best ones. And in that time, sort of rocket fuel being a high energy substance actually doesn't stay good for very long. It has an expiration date. So you want to land a rocket and launch it as soon as you can. It already has to survive the trip to Mars. So the idea is that once the rover is finished caching all of its samples, which could be, I don't know how many years that's expected to take, there will then be a second mission to bring them back. And that one's going to be done by the European Space Agency. And so it's going to be a few years before that one launches. I don't know if they've set a launch window for it. But yeah, it's going to take a while. The Perseverance rover just landed. I'm not sure if they've even cached their first sample yet, but they're going to take their time. They're going to analyze. It carries with it a suite of analytical techniques to make sure that their samples are going to carry the most science. They're going to be extremely, extremely difficult to get a sample back from Mars. So we want to make sure that the ones we do bring back are worth the effort.
Mm-hmm.
I just Googled an article and it said 2031 was about the earliest time they thought they'd be coming back. So
that sounds about right.
Okay, Scott would like to know, what are the outer limits of temperature and pressure at which we think life could persist? Recently, I haven't checked this, there was rumor about tardigrades not being tough enough to survive falling through the atmosphere. What are the prospects for simpler life surviving a journey from one planet to another carried by this cosmic Uber that Arianna talked about?
Let's see, well, a couple different points to make there. I think some of these Ubers they're different sizes. And so you can actually carry material from one place to another if it's large enough. And during the re-entry or the entry process through an atmosphere, such as our Earth's atmosphere, it does cause quite a bit of degradation. Certainly there's a shock layer that forms for over 30, 40 minutes, and that will essentially disintegrate parts of the material. But we have proof that some of that material survives and continues to fall, and then we find it. So I think there are different ways in which the actual host material, the meteorite or the rock, and the minerals themselves are up to the task for survival. In terms of temperature or pressure conditions out at the extreme edges, maybe of our solar system and the like, it's a pretty inhospitable place. It's cold. I wonder if maybe Dr. Walrath has a better idea of sort of in the outer solar system, what the conditions are there. I think the simple maybe prebiotic materials can exist quite easily, but it really is through this insertion of some energy source to build up something more complicated. You need a process. I don't know, Dr. Walrath, do you want to comment?
So this question is on survivability of life. Then life can actually be pretty sturdy. And then it's a question of, what counts as survival? Like if it's a bacteria that's fragmented to the point that it's, maybe it itself is not necessarily alive anymore, but it can also seed the growth of new things which can feed off of it. In terms of life forming, it's a question of scale as well. Like if you just have a small meteorite, which happens to have some liquid water and some sort of like maybe something's decaying radioactively on it, providing some heat, but it's such a small thing that it's only going to have very few reactions going. You need sort of like, it's as far as we know, it's a game of chance. So you need a large volume of reactions all ongoing to have a large enough chance to produce the spontaneous formation of life. Also, in terms of life surviving the trip, we know that the core of a meteorite can actually stay pretty cold, surprisingly, as it descends through the atmosphere. So it's entirely possible that if there's like a very large enough meteorite that it doesn't completely evaporate in the atmosphere, then, who knows? It could be possible that some chunk of it flies off and loses enough speed that it doesn't impact. I mean, we pick up these meteorites and they're, you can find them and see them in museums and stuff, and they're not all turned into dust. So it could be that something in the core of one of those survives, but probably for that there would have to be life outside of the Earth, and that's a completely different question. So.
Could I just jump in there? I see a couple of questions that maybe this kind of all touches on about, is the main theory still that that life is developing in oceans? And I correct me if I'm wrong, but I think what we're saying is that on these meteorites, these Ubers might be delivering the ingredients of life or the building blocks of life, but it's not a very common hypothesis that, coronavirus or some bacteria is living on a meteorite that then lands on Earth and that seeded life, right? We're talking more about chemistry occurring to produce the building blocks, but then we believe through those evolutionary processes in the oceans or bodies of water, that's where it's happening. Is that correct?
Yeah, I believe so. Richard Walrath is probably more expert than myself, but I think there's another piece here as well in the impact process itself, and then the remnants or the modification of the surface during that impact event. There's a lot of opportunities there, especially for key mineralogy to play a role. And then you build on top of that opportunities for these microorganisms that are happy with extreme conditions, right? These extremeophiles. And so you can sort of have a combination of these sequences take place that then promotes more opportunities. Yeah.
Okay, Yuli would like to know, how do these spatially relatively loose bunches of electrons from the Linac produce much tighter X-ray pulses from the LCLS? What is the magic that compresses the X-ray pulses?
Oh,
what is the scale of compression?
That is a great question. I think Professor Sandberg is key to answer that one.
I'm excited to answer that one.
I know.
Thanks, Julie. Yuli, that's a great question. And that's one of the, I won't call it magic, but that's the word I want to use about these X-ray free electron lasers, is you get, like you described, this kind of loose bunch of electrons that in science we'd call it, they're incoherent. They're all doing their own thing, except they're all traveling along this long accelerator, like Dr. Gleason showed, at near the speed of light, very near the speed of light, like 99.999% the speed of light. And then we pass them through these magnets that jerk them back and forth. And as we do that, they're accelerating. And when we accelerate electrons, they produce light. And now this light is starting to interact with the charged particles. And it's that interaction of the light with the charged electrons, which then starts causing the electrons to start going towards the peaks and the troughs. It's actually not the peaks and troughs, but it's the peaks and troughs in that light wave start pushing the electrons together. And so the electrons start self-organizing. And it's a feedback of the X-rays that are produced on the electrons, which then causes the electrons to produce X-rays that are more laser-like. And so it's this really beautiful feedback. And it builds up exponentially, and it's a lasing process. The technical term is called self-amplification of spontaneous emission. So those first X-rays that are generated are kind of spontaneous, but then they cause the electrons, as they interact over this really long magnetic array called an undulator. It's about a football field long. And that's what causes the electrons to get squished together and organize and then produce laser-like X-rays.
Yes, very early in this series, when the LCLS first turned on, we had a lecture on how the LCLS works. The title was ZAP, the X-ray laser is born. It's actually a great lecture. And if you go to the SLAC website, the public lectures website, and click on past lectures, you can look it up. So I'd recommend it. Probably we ought to have another lecture like that, now that that one's 10 years old, to tell you about what's happened in the meantime, but that's a whole nother question. I'm going to lob a softball question at Arianna.
Sure.
I would like to know that if we can reach the plasma stage of matter using lasers, how much additional energy would it require to reach the nuclear fusion stage? And could this actually play a role in biology? I think the answer to that last question is no, but the first one has an interesting answer.
Yeah, the second part is probably no, but I think deposition of energies, much like what we have leveraged at the NIF. So there's the National Ignition Facility here, also in the Bay Area at the Livermore National Lab. So there they use 192 lasers, all pointed at essentially just the tip of a pen. And this with very strategic targets or sample materials, you can actually start this this process, this mimicking the interiors of a star. And so here at SLAC, one thing that we're looking forward to for the MEC, the Matter in Extreme Conditions Hutch, is in fact an upgrade in our lasers, our drive lasers, of which I really just mentioned one, or to generate the shockwaves. But there are other tools, other types of lasers that can be leveraged, so-called short pulse lasers that actually deliver higher intensity in a different spatial regime. So you generate these plasmas. And I think that there are a couple opportunities we're looking forward to as a community, where key upgrades to parts of our laser system here will get us to that next step. And then we can actually do maybe some of the experiments you're thinking about in our upgraded laser facility. I know that also Professor Sandberg is playing a key role in having the community be active and aware in this possible upgrade opportunity.
Yes, this is actually a screenshot of a rendering behind me of the proposed upgrade to the Matter in Extreme Condition Hutch.
Oh, I didn't know that. It's cool.
Yeah, sorry, I got permission from Alan. I don't know if he's still on, but
okay.
Yeah, so we're really excited about that, and the MEC has really changed a lot of our understanding. And there's, I think, more than a handful of facilities around the world that have kind of jumped into that game now, in Germany and Japan and Korea, China, where they are trying to improve upon or duplicate the results at MEC. And so there's kind of this race now to see who can combine these really brilliant X-rays with these higher energy and denser states of matter. And so the MEC upgrade would be really exciting, a big push forward for the United States high energy density physics community, and a really big improvement for SLAC. So we're hoping it happens on the order of the next 5 to 7 years.
Okay, so let me ask you now a final question. And this one is maybe more philosophical, but you might have something to say about it. Someone wants to know, does this work help us to understand the other aspect of life that we're extremely interested in now, namely the effect of climate change and the impact of human behavior on climate change? So this person asks, how can the search to understand the origins of life help us to take better care of the life on this planet?
Oh, that's a wonderful question. I think part of the answer there is really engaging in the appropriate scientific studies to visualize these fundamental chemistry and physics experiments that tell us the story of that sequence as it builds up to form possible life. The climate change aspect is one in which we can monitor now, unfortunately, in real time in a number of ways, how our environment is being modified by our activity. And we can actually zoom in on some of those, changes in the chemistry and changes in biology that we see as a consequence. And again, it's really coming down to some of those fundamental physics and chemistry studies that enable us to see, oh, you know what we did wrong here, or you know what the consequence of this, you know, process that maybe we kickstarted is modifying the biology in the following way. And so it's a visualization sort of revolution that we can actually see and distinguish these now. And hopefully it will help us do a better job at protecting the life that we have here. I'd also like to give maybe both Dr. Walrath and Professor Sandberg an opportunity to pitch in here. Maybe Dr. Walrath first.
Yeah, definitely agree with all that you said, and yeah, it's definitely, I definitely wouldn't say it's directly related to work on climate change or how to prevent it. Understanding this, you know, there are some like looking at, you know, how these things form in these types of plasma events. It's related in some ways to the types of reactions that happen in combustion, which is, you know, how we still derive a large portion of our energy, and could potentially, you know, if we can close the carbon loop, and some people looking at, could we capture CO2 and turn that back into fuel? So understanding that chemistry in these conditions might, you know, help us to understand chemistry in these other ways. And there is work, I believe, work done at LCLS to look at combustion, which is itself a very complicated process. You don't think of it, but the chemistry happening in your car engine is actually not that well understood. So maybe we can find ways to be more efficient and reduce our carbon footprint that way. And then this provides just a new way for us to, you know, sort of synergistically understand the origins of life, and also how to have practical applications.
Yeah, just to build on Richard and Ari's comments, you know, the understanding of this high energy density state may not directly tie into climate change, but a lot of the work done at the national labs is. Dr. Walrath mentioned some there. I'll just mention a lot of the work done at MEC, and some of the big motivation for the upgrade is to understand fusion energy. And if we can master that and get that working, that will be essentially limitless clean energy, which could make a huge dent. We could drastically reduce our dependence on fossil fuels if we can get fusion energy working. So that is definitely related with this matter in extreme condition. And I guess just for me personally, understanding how intricate the origins of life is makes me personally appreciate it more and want to take more personal care of it, right? To do my part to make sure that we are preserving and protecting life here, because we can see how quickly species can disappear and then we don't get them back. So yeah, I think when I study the origins of life, or think about that process and think it could be building blocks of that could be coming from stars, could be coming from meteorite impacts all over, raining down, combining in our ocean over billions of years, I think, wow, this is precious. Maybe just one other comment about a question I saw there in the discussion that, oh, I forgot it now, sorry. So I'll read through the comments and I'll come back to that. But yeah, understanding this makes me appreciate life. And it's not unique. We believe there are other sources of life out there, other exotic, interesting things. Oh, that was a question, is why haven't we detected them yet? Well, I guess my answer to that would be space is really big. And just in the last few years, we've discovered how to find planets that are out there. So some of these planets are so far away, even if they had, you know, radio as soon as we did, we may not have gotten those messages yet. So it takes a while for those signals to go across space.
Well, look, thank you all very much. It's been a wonderful lecture and a very interesting discussion. You can't hear the people out in the audience, but I think that they very much appreciated this conversation. So thanks a lot. Thanks to all of you who came. And as I said, we will have another of these public lectures toward the end of July. And if you're on the mailing list of the SLAC public lectures, you'll get an announcement of it in good time. And so thank you all.
Thank you very much. And my special thanks to Dr. Walrath and Professor Sandberg for joining us this evening. Thank you so much.